A differential equation for capacitor charging in an RC circuit. Here we will derive an equation for Q of t on the plates for a charging capacitor. With reference to the figure, starting at the dot, taking into account the assumed current I and proceeding clockwise, the Kirchhoff's loop equation is right there. E minus IR minus VC is equal to 0. We're first going to modify that equation in these ways. We're going to change I to dq dt. We're going to change V sub c to Q over C. Let's do that. E minus dq dt times R minus Q over C equals 0. What is it about the part A answer that makes it a differential equation? And to review, hopefully, a differential equation has both a variable and a derivative of that variable in it. And that is what we have in that equation. You can see we have Q here, and then we have the time derivative of Q. So that is a differential equation right there. Now we're going to solve this differential equation. We're going to rearrange that answer so that we have R and dt on the left, and dt is going to be in the numerator. So there's our differential equation. And if we arrange that so that only R and dt are on the left with dt in the numerator, I'm not going to take the time to do this, but this is what the answer comes out to. dq over E minus Q over C. Stop the video if you need to, but that's what you get to get dt and R on the left with dt in the numerator. We're going to integrate both sides here. We're going to integrate the left side with respect to time. We're going to go from time equals 0 to some later time t, dt over R. And on the right, since we're charging this capacitor, the initial amount of charge is going to be 0. Later, it's going to have some non-zero amount of charge, dq in the numerator, epsilon minus Q over C in the denominator. All right, we're going to use U substitution to solve this, and U is going to be the denominator here. So U is equal to epsilon, or big E, right? That's the voltage of the battery, minus Q over C. We're now going to differentiate this to get du dq. So du dq. You differentiate that voltage term, you just get 0. You differentiate the next part with respect to Q, and you get negative 1 over C. We're now going to solve this for dq. dq is going to equal negative C du. All right, moving right along. We're going to substitute the answers from parts E and G into the answer to part B. To save time, I've recopied those. There is our part E answer right there. There's our part G answer. And a little bit earlier, our part D answer, I'm trying to save space here, looked like that. So we want to substitute those things in there. What is that going to look like? Well, the left side is going to be unchanged. We're going to go from t equals 0, t equals t, dt over R. But what about the right side? I'll go ahead and leave those integration limits in there. But on the right side, we have this epsilon or E minus Q over C in the denominator. So that means that there's got to be a U in the denominator. Put a fraction there. And then dq is right over here on the left. Opposite C du. Opposite C du. So far, so good? All right. Now, we're going to mentally integrate the left side of the part H answer. So let's do that. If we integrate this with respect to time and include those limits, that is simply t over r. T over r. And we're going to move all the constants to the left side. This C is a constant. That's going to go on the left side. So let me put that next to the R. I'll go ahead and put the negative sign over there. And everything else on the right is unchanged, like that. Now we're going to integrate the right side of part I, and we're going to unsubstitute the part E answer, which once again is this right here, so that there aren't any more U terms, only Q terms. The left side of the equation will be unchanged, negative T over RC. And then on the right side, when we integrate du over u, we get the natural log of u. And what's u? Down here at the bottom of the screen, u is big E minus q over c. And the limits are from q equals 0 to q equals q. Well, I'm thinking we're going to have to evaluate those limits in the next step. And sure enough, how about that? Let's evaluate the limits, and then we're going to use a law of logarithms to kind of make that look a little bit simpler. The left side, once again, is unchanged, minus t over rc, and then we're going to put q in there for q, and then we're going to put 0 in there for q. So I think we're going to get the log of e minus q over c in the numerator, and then in the denominator, we'll just get e. And there's our law of logarithms, where subtracting logarithms and dividing logarithms gives you the same sort of thing. Well, let's rewrite this so that we have 1 minus something on the right. Negative t over rc is equal to the log of, I put absolute value signs here because you can't take the natural logarithm of a negative number, so that would have to be a positive number. And there's e right there. All right. Now we need q. That's what we want an equation for. So let's get rid of the natural log by doing e to the both sides here. And then we're going to solve this for q. How can we do that? Let's put the q on that side. So if I show a little bit of work here, we end up with q over ce on that side. And on the right side, we get 1 minus e to the minus t over rc. And so I think, oops, you couldn't see that very well. I think our expression for q is going to be c times e 1 minus e to the minus t over rc. There you go. What does this tell us? Initially, how much charge should there be on a capacitor? Initially, there should be no charge on a capacitor. So if I put a 0 in there for t, e to the 0 is 1. 1 minus 1 is 0. Sure enough, this equation tells us that initially there will be no charge on the capacitor, and at time is equal to infinity, e to the minus infinity is 0. So the amount of charge on the capacitor at time 0 is 0. The amount of charge on the capacitor at time infinity is numerically equal to C times E, which E, remember, is a voltage, so that's kind of like C times V, and that's an equation that we ran into a long time ago. Capacitance is Q divided by V, and that's essentially what you're doing right there.